The United States Air Force and NASA studied the feasibility of a nuclear pulse spaceship between 1950s and 1960s called Project Orion. The spacecraft would be directly powered by a succession of atomic explosions that would occur behind it. The vehicle was once intended to be able to take off from the ground. Later iterations were only intended to be used in space. Dr. von Braun, who published a white paper endorsing the concept, was among the proponents of the design work, which was carried out at General Atomics in San Diego. Models were used for non-nuclear testing, but the project was ultimately shelved due to a number of factors, including worries about radioactive fallout and the 1963 Partial Test Ban Treaty, which prohibited nuclear explosions in space. The general concept of nuclear pulse propulsion was first forth by physicist Stanislaw Ulam in 1946, and Ulam and Frederick Raines performed preliminary calculations that were documented in a 1947 memo from Los Alamos. Ulam co-authored a confidential report in August 1955 that suggested using nuclear fission bombs ejected and detonated at a considerable distance to power an orbiting spacecraft. Ted Taylor of General Atomics oversaw the project, and scientist Freeman Dyson took a year off from the Institute for Advanced Study in Princeton to work on it at Taylor's request. When DARPA decided to fund Orion at a starting annual budget of $1 million in July 1958, the project officially got underway and was given a name. General Dynamics Corporation was given permission to explore the idea by the government, but in late 1959, the agency made the decision to stop supporting it. Nuclear physicists and mathematicians that worked at the project managed to develop the Taylor-Ulam design of thermonuclear weapons, found the idea of a cellular automata. He made various conjectures and established a few theorems in both pure and practical mathematics. In order to create the first nuclear bombs during World War II, a research and development effort known as the Manhattan Project was started. Leading the charge was the United States, working with the United Kingdom and receiving assistance from Canada. The US Army oversaw the project from 1942 to 1946. Robert Oppenheimer oversaw the Los Alamos laboratory, which created the bombs. 10,000 kilometers per second velocities were possible thanks to the Orion concept's tremendous thrust and high specific impulse or propellant efficiency. At the time, it was thought that a nuclear device of a moderate size could generate 5 or 10 billion horsepower. External detonations would be used to control the extremely high power of the nuclear explosions in relation to the mass of the vehicle. An earlier iteration of the pulse concepts suggested trapping the blasts in an interior pressure structure, with one such design created by the Martin Company. To put it in qualitative power terms, electric ion engines create a tiny amount of thrust very effectively, while traditional chemical rockets, like the Saturn V that launched the Apollo program to the Moon, produce enormous thrust with low specific impulse. In contrast, Orion would have provided performance higher than the most sophisticated nuclear or conventional rocket engines that were being considered at the time. Proponents of Project Orion believed it may pave the way for inexpensive interplanetary travel. A common concept for both very high-performance interplanetary flight and interstellar flight without external power beaming is the use of external nuclear pulse propulsion to maximize survivable power. This idea has been present in serious concepts for projects ranging from Project Longshot to Project Daedalus, Mini-Mag Orion, and other proposals that reach engineering analysis level of considering thermal power dissipation. Compared to Project Orion's bigger nuclear pulse units, such later suggestions have tended to tweak the basic premise by imagining apparatus driving the detonation of much smaller fission or fusion pellets. Meganewtons of thrust are combined with an extremely high exhaust velocity between 19 and 31 kilometers per second in typical interplanetary designs in the Orion nuclear pulse drive. Nuclear pulse rockets are the only technology that has been presented that may be able to match the extremely high power needs needed to supply both at once, even though many spacecraft propulsion motors may only accomplish one of these goals. The Orion concept explodes nuclear explosives outward at a power release rate that exceeds what interior nuclear reactors could withstand with currently available materials and designs. Because weight is not a constraint, an Orion craft can be quite sturdy. A vehicle without crew could withstand extremely high accelerations, up to 100 g. In contrast, an Orion manned by people needs to employ some kind of dampening mechanism behind the pusher plate to reduce the nearly instantaneous acceleration to a level that is manageable for humans, usually between 2 and 4 g. To optimize the rocket's force per mass of propellant, high exhaust velocity is necessary for good performance. The square root of the nuclear fireball's temperature change determines the velocity of the plasma debris. Such fireballs produce exceptionally high velocity because they can reach temperatures of 10 million degrees Celsius or higher in less than a millisecond. A workable design must also restrict the fireball's destructive radius. The square root of the bomb's explosive yield determines the nuclear fireball's diameter. Efficiency depends critically on the reaction mass of the bomb's form. The initial project created bombs with tungsten reaction masses. The reaction mass was struck by the concentrated X-rays and plasma from the nuclear explosive's core due to the bomb's design and composition. All bombs would essentially be nuclear-shaped charges. When a bomb with a reaction mass cylinder bursts, the plasma expands into a flat, disc-shaped wave. A much more effective cigar-shaped wave of plasma debris is produced when a bomb with a disc-shaped reaction mass expands. A large portion of the plasma is focused onto the pusher plate by the cigar-shaped structure. The rocket equation requires that, rather than being spent isotropically, the majority of the bomb's explosive force be directed toward the spaceship in order to maximize mission efficiency. Each impulse will be smaller in a smaller bomb, meaning that the rate of impulses will be higher and more than what is required to reach orbit. Less G-shock on the pusher plate and less need for dampening to even out the acceleration are two other benefits of smaller impulses. For the 4,000-ton human-crewed reference design, the ideal Orion drive bomblet yield was estimated to be around 0.15 kiloton, requiring about 800 bombs to orbit at a rate of about 1 per second. It became clear in late 1958 or early 1959 that the smallest attainable bomb yield would define the smallest vehicle that could be used. The mass of the vehicle would be 880 tons if 0.3 kiloton bombs were used. This was thought to be too small, though, for anything beyond an orbital test vehicle, so the researchers quickly turned their attention to a base design that would weigh 4,000 tons. The specifics of tiny bomb designs were unknown at the time. Before being released, many Orion design reports had all explosive details removed. The Super Orion design, which weighs 8 million tons and could easily be a metropolis, is the largest of the designs above. The designers discussed the idea of the massive ship serving as an interplanetary ark in interviews. It was possible to construct this radical design using methods and materials that were either readily available in 1958 or were expected to become so soon after. The majority of the 3,000 tons of each Super Orion propulsion unit would be made of inert materials, including boron salts or polyethylene, which would be utilized to absorb neutrons to reduce fallout and transfer the force of the propulsion unit explosion to the Orion pusher plate. Freeman Dyson had one design for the Super Orion that called for the pusher plate to be mainly made of transuranic elements, like uranium, so that it could be converted to nuclear fuel when it got to a nearby star system. The performance of the Orion nuclear pulse rocket design is quite high. The original intention was to employ Orion nuclear pulse rockets with nuclear fission-type pulse units for interplanetary space missions. In the initial version of the concepts, single-stage missions to Mars and return as well as a visit to one of Saturn's moons were planned for an Orion vehicle. The first analysis of the types of Orion expeditions that could reach Alpha Centauri, the closest star system to the Sun, was carried out by Freeman Dyson. Dyson's 1968 work Interstellar Transport kept the idea of massive nuclear explosions, although he thought about using 1 megaton deuterium fusion explosions rather than fission bombs. His findings were straightforward. Orion's hemispherical pusher plates, reflecting design, would lower the debris velocity of fusion explosions from 3,000 to 30,000 kilometers per second to 750 to 15,000 kilometers per second. Dyson looked at 2 spacecraft designs to get an idea of the high and bottom bounds of what could be accomplished using 1968 technologies. The more cautious energy-limited pusher plate design only needed to completely absorb 4 by 10 to the 15 joules of thermal energy for each impinging explosion, of which the pusher plate would absorb half in order to prevent melting. Dyson calculated that the diameter and mass of the hemispherical pusher plate would need to be 20 kilometers and 5 million tons, respectively, if the exposed surface was made of copper with a thickness of 1 m. Before the next explosion, the copper would need to radiatively cool for a duration of 100 seconds. The energy-limited heat-sink Orion design would then take an order of magnitude longer to reach Alpha Centauri. Dyson thought of an alternate momentum-limited pusher plate design, where an ablation coating of the exposed surface is replaced to get rid of the extra heat, which would increase performance while decreasing size and cost. The ability of shock absorbers to transfer momentum from the pusher plate that accelerates impulsively to the vehicle that accelerates smoothly then sets the limits. Regardless of the size and type of explosion, Dyson calculated that the qualities of the materials available limited the velocity imparted to about 30 meters per second. The pulse rate is 1 explosion every 3 seconds if the vehicle is to accelerate at 1 Earth gravity with this velocity transfer. Subsequent research suggests that the maximum cruising velocity achievable in theory is only a small percentage of the speed of light. Orion atoms fission at a speed of about 9 to 11% the speed of light is possible. Based on fusion antimatter catalyzed nuclear pulse propulsion units, a nuclear pulse drive starship may reach velocities of around 10%, whereas pure matter antimatter annihilation rockets might theoretically reach up to 80% of the speed of light. Saving fuel to slow down reduces the maximum speed in each scenario. An alternative to using propellant to slow the spaceship down as it gets closer to its destination is the idea of deploying a magnetic sail, which would enable the ship to approach the maximum theoretical velocity. Not including the time needed to attain that speed, Orion thermonuclear starships would need to fly for at least 44 years at 0.1 C to reach Alpha Centauri, or roughly 36 years at a constant acceleration of 1 g. It would take an Orion spaceship 100 years to travel 10 light-years at 0.1 C. This is a great use for nuclear weapons stockpiles, according to astronomer Carl Sagan. In 1973 and 1974, the British Interplanetary Society proposed an idea that was comparable to Orion. Project Daedalus was designed to be a robotic interstellar probe that would reach Barnard's star at a speed of 12% of c. Project Longshot, conducted in 1989 by NASA and the US Navy, looked into a similar idea. Unlike Orion, none of these concepts can be implemented at this time because they both require considerable advancements in fusion technology. The cost of the fissionable materials needed was formerly believed to be significant, but scientist Ted Taylor demonstrated that, with the correct explosive designs, the quantity of fissionables needed for launch was nearly constant for all Orion sizes. The larger bombs were more efficient because they supercompressed the fissionables with more explosives. Additionally, the extra explosion debris provides mass for propulsion. The current version of the Partial Test Ban Treaty of 1963, which forbids all nuclear detonations, except those carried out underground in an effort to slow the arms race and reduce the amount of radiation in the atmosphere caused by nuclear detonations, the US government attempted to include an exception to the 1963 treaty that would have permitted the use of nuclear propulsion for space travel. But Soviet concerns about the treaty's potential military uses prevented this from happening. The USA, Russia, and the UK would be the only countries impacted by this restriction. Additionally, it would be against the de facto ban on nuclear testing that the declared nuclear powers have enforced during the 1990s, as well as the Comprehensive Nuclear Test Ban Treaty, which China and the United States have both signed. An electromagnetic pulse produced by the launch of an Orion nuclear bomb rocket from the ground or low Earth orbit may seriously harm computers and satellites, as well as fill the Van Allen belts with high-energy radiation. Launching from extremely far locations might potentially fix this issue, as the EMP footprint would only be a few hundred miles across. To quickly eject the energetic particles from the Van Allen belt, a few relatively modest space-based electrodynamic tethers could be deployed. Non-nuclear techniques could be used to accelerate an Orion spacecraft to a safer distance, only then starting its drive far from Earth and its satellites. Theoretically, there are two excellent solutions: a space elevator and the Lofstrom launch loop. For the space elevator, the current carbon nanotube composites, possibly with the exception of colossal carbon tubes, do not currently have enough tensile strength. When launching big masses into orbit, all chemical rocket designs are incredibly inefficient and costly, although they might be used if the outcome was more affordable. The majority of the 3,000 tons of each Super Orion propulsion unit would be made of inert materials, including boron salts or polyethylene, which would be utilized to absorb neutrons to reduce fallout and transfer the force of the propulsion unit explosion to the Orion pusher plate. Freeman Dyson had one design for the Super Orion that called for the pusher plate to be mainly made of transuranic elements, like uranium, so that it could be converted to nuclear fuel when it got to a nearby star system. The performance of the Orion nuclear pulse rocket design is quite high. The original intention was to employ Orion nuclear pulse rockets with nuclear fission-type pulse units for interplanetary space missions. International cooperation is becoming more commonplace in many respects, and it is possible that this cooperation could extend to the peaceful use of nuclear pulse technology. It does offer a useful means of getting rid of the huge global stocks of fissionable material, suitable for use in weapons, and if utilized at a sufficient distance within low Earth orbit, the environmental pollution would be negligible. There is little doubt that persuasive technological need and international cooperation would be necessary for political adoption of such an initiative. There are already a number of propellant concepts that could be applied to human Mars missions. Nonetheless, using conservative estimates of technological preparedness, 2 to 3 year supply rations would be the limit for these expeditions. If it became necessary to launch a Mars mission considerably more quickly, in a year or less, or if it became necessary to deliver heavy payloads or people as quickly as possible to locations in the outer solar system, such Jupiter and beyond, using nuclear power becomes increasingly compelling. If these operations required a great deal of international collaboration, then this kind of technology might be more widely accepted. The direction of micro-fission processes may be the most promising avenue for the application of fission-based nuclear pulses. These systems include compressing subcritical targets of fissile material using a spaceship mechanism, which is akin to fusion-based notions. The primary distinction is that a fission sample requires a lot less energy to push it to supercriticality and large burn-up percentages than a similar fusion process would. This kind of strategy has obvious benefits. It removes the worries about having cars that are actually loaded with bombs. These devices cannot be utilized as weapons in any traditional sense because they depend on the spaceship for their compression and energy supply. Not only does this address the worry about keeping thousands of tiny bombs in close proximity to each other, however, it also eliminates a great deal of the issues related to nuclear air propulsion. There are not many research that have been done using this strategy. However, the outcomes are highly promising. It might turn out to be a more practical transitional step between today's propulsion technology and tomorrow's proposals for fusion propulsion.